So section 7.2 is graphing rational functions. Rational functions is any function in the form p of x over q of x, where p and q are polynomials and q of x cannot be 0. The parent function for simple rational functions is f of x equals 1 over x. So it's basically any function that is written as a ratio or a fraction, and specifically you have to have at least like x in the denominator to make it a rational function. So for example 1, let me backtrack a little. Usually like in person in class, this would be like something that I would have you guys like work through on the table, create the table and the points for on your own, and then we would kind of go through and talk about the intricacies of each problem. So if you want, you can pause the video here if you have it printed and kind of go in and fill in the table and get the points. If not, just keep playing it and follow along. So example 1 is graph f of x equals 1 over x. So we're given all these x values, we're going to find the f of x value for each one. So when x equals -3, f of x or f of -3 would be 1 over -3 or -1/3. When x equals -2 would be 1 over -2 or -1/2. 1 over -1 or 1 over -1 would be just -1. 1 over 0 would be undefined, where you can't have a fraction, or you can't have a 0 in the denominator of a fraction. And then 1 over 1 is just 1. 1 over 2 is 1/2. 1 over 3 is 1/3. So we'll worry about this stuff in the middle at the bottom after. We're just going to graph the function for now. So 3, -1, or -3, -1/3. Just do your best to graph it as accurately as possible. So left 3 and then down about 1/3. And then -2, -1/2. So left 2 down about 1/2, so a little bit further from 1/3. And then -1, -1. So left 1 down 1. And then we have a point at 0, or 0 is undefined, and then we have a point at 1, 1. We have a point at 2, 1/2. And we have a point at 3, 1/3. So we have to think about like, especially like, or we'll just kind of focus on the positive x values. So like if I kept going up with x, like did x equals 4, x equals 10, even x equals 20, all of those values would go in the denominator. So it'd be like 1/10, 1/20, but it would never be 0. So the higher the x value gets, just the closer this line is going to get to the x-axis. It's going to get infinitely close without ever actually crossing it, because no matter how big of an x value I put down here, this number is just going to get smaller and smaller and smaller without actually equaling 0. And then same idea, because like when x equals 0, or yeah, when x equals 0 is undefined, that also means that we're never going to have a point on the y-axis, because that's where x equals 0. So these lines are going to get infinitely close to the y-axis as well. So how they look on a graph is they get very, very close to each axis without actually crossing them. I got really close on that top part, I didn't mean to. And then same thing down below in the third quadrant. So we're getting infinitely close to the axis without actually ever crossing it. And then on these graphs, on rational functions graph, we have things called asymptotes. So asymptotes are just like these lines that the graphs will get infinitely close to, but they'll never cross. So on the parent function, on f of x equals 1 over x, we have an asymptote at x equals 0, which happens to be the y-axis. And then also at y equals 0, which happens to be the x-axis. So the function is undefined at x equals 0 and also at y equals 0, because there's no way for us to get like a f of x or an output of 0, because no matter what x value you put in here, nothing is going to make this fraction become 0. So at x equals 0 and y equals 0, and then an asymptote again is a line that the graph gets very close to but never touches. So asymptote, a line that the function approaches but never crosses. And then down at the bottom we'll talk about domain or asymptotes and domain and range. So the horizontal asymptote, any horizontal line would start with y equals. So it's y equals 0 in this case is my horizontal asymptote. If it was up here, it'd be like, say, y equals 5 is any horizontal line, and then any vertical line starts with x equals. I know sometimes it seems like it should be the opposite. So x equals 0 would be my asymptote here. It's anywhere along this line. If this line were to move left or right, this could be like x equals 3 right here because all the x values are 3, and so on. And then for domain and range, it's almost all real numbers, but there is kind of some issues because of the asymptote. So how we write the domain is, let's say x is within the set of all real numbers. I'm going to rewrite that, that's a little ugly. So this is saying x is within the set of all real numbers, except, because x cannot be 0 since we have a vertical asymptote at 0, so x cannot be 0. So one more time, this says x is within the set of all real numbers except x cannot be 0. And then for the range, it's a similar idea, but instead of x, it's now f of x. So f of x is within the set of all real numbers too, except f of x cannot be 0 because we have a horizontal asymptote at y equals 0. So because if we look at all the possible x values, it looks like it goes on forever here. It gets really, really close, like to the y-axis here, so close to x equals 0. And then it gets really close on this side, infinitely close, and infinitely close right here. Or, sorry, the x values continue on infinitely to the right. So it's pretty much all real numbers, except it just can't be 0 because of these vertical and horizontal asymptotes. Okay, so the next graph g of x equals 4 over x. So same thing, we'll fill in the table for this function. So g of negative 3 would be 4 over negative 3, so negative 4/3. G of negative 2 would be 4 over negative 2, so negative 2. And then 4 over negative 1, so negative 4. And then 4 over 0, so again that's undefined. And then 4 over 1, so 4. 4 over 2, so 2. And 4 over 3, so 4/3. And then we can plot those points again, so negative 3, negative 4/3. Negative 4/3 is like negative 4 1/3. So, sorry, excuse me, negative 1 1/3. So negative 3, and then down 1 1/3. And then for negative 2, left 2, down 2. Negative 1, negative 4, left 1, down 4. And then 1, 4, right 1, up 4. 2, 2, right 2, up 2. And then 3 4/3, so right 3, and then up 1 1/3. And then the graph will be a similar shape, except now think about like what happens when we have kind of a coefficient out in front of things that stretches out the graph. So it pulls it away from the x-axis. It's still eventually going to finish infinitely close to the x-axis, just right now it's pulled away from it more than the parent function because of that 4 in the numerator instead of a 1. So because the graph hasn't shifted at all, like shifted left, right, up, or down, it's just been stretched, then there's still asymptotes in the same exact spot. So there's still a vertical one at x equals 0. And then a horizontal one at at y equals 3. So our horizontal asymptote, this one right here, is still y equals 0. And our vertical asymptote, this one right here, is still x equals 0. And then because our horizontal and vertical asymptote haven't changed, neither have our domain and range. So domain and range are directly dependent on the asymptote because those are the only restrictions that are created. So the domain is still all real numbers, or sorry, x is within the set of all real numbers except x cannot be 0. And then same idea for f of x or y. F of x is within the set of all real numbers, except f of x cannot be 0 either because of the asymptotes. So we're saying there's a horizontal asymptote at 0, that means f of x or y just literally can't be 0 because it'll never cross that line. And then one more time just to kind of talk about domain and range again, it's almost like literally almost all real numbers. It's because like our x values will go on forever infinitely right here, like to the negative side, but then they'll get very, very close to 0 right here, like just fractions of a value. And then on the upper side, we're gonna get really, really close to like the x-axis here, so very, very small and very close to 0, but then go on infinitely to the right. And y does the same thing, like my y values go up infinitely here but get extremely close to the x-axis. They're extremely close to the x-axis here, so super close to 0, and then just go down infinitely. And then the next one, example 3, is k of x equals 2 over x minus 3 plus 1. So even though like rational functions definitely look different than the ones we've studied before, what's cool is transformations work pretty much the same way when it's in this form. So we're subtracting a number away from x, that means we're going right 3. We're adding a number after, that means we're going up 1. So since we're translating right 3 and up 1, we have to shift our asymptotes. So if we're moving right 3, that means our vertical asymptote that would normally be right here at x equals 0 is going to shift over to x equals 3. It's going to move 3 over. And then that means that our horizontal asymptote is going to shift up 1. So it's going to go up 1 from 0. So our vertical asymptote is going to shift right 3, and our horizontal asymptote is going to shift up 1. Oops. And you can draw them ahead of time if you want. You can wait till after, it's up to you, but it's shifting. Our vertical asymptote starts at 0, or x equals 0, and it shifts over to x equals 3. And then our horizontal asymptote starts at y equals 0, and it shifts up 1. So drawing those asymptotes can kind of help you figure out what points that you want to use on your table. The one thing that I like to do for the table is to have, I mean, you notice there's like 7 points on it, but one of them is undefined. So whatever your vertical asymptote is, should be in the middle of your table. So whatever the x value is of your vertical asymptote, in this case it's x equals 3, that should be in the middle of your table, and then you should go up and down from there, and that'll give you the best points. So down to 2, 1, 0, and then up to 4, 5, 6. That way you get points on either side. So when x equals 0, we'll substitute that in here. So 2 over, that'll become negative 3 plus 1. So negative 2/3 plus 1 is positive 1/3. And then 2 over 1 minus 3, so over negative 2 plus 1, that's like negative 1 plus 1, so 0. And then 2 over 2 minus 3, so negative 1 plus 1. Just plugging in all these x values into the function itself. So 2 over negative 1 is negative 2. Plus 1 is negative 1. When I substitute in negative 3, I get 0 in the denominator, so that's undefined. When I plug in 4, I get 2 over 4 minus 3, so over 1 plus 1, so 2 plus 1 equals 3. When I substitute in 5, I get 2 over 5 minus 3, so over 2 plus 1, so 1 plus 1 is 2. And then when I substitute in 6, I get 2 over 6 minus 3, so 3 plus 1. So 2/3 plus 1, you can write it as 5/3, you can write it as 1 2/3, whatever is easier for you to graph. Okay, so 0, 1/3, so I'm not going left or right at all, I'm just going up 1/3 for that first point. And then 1, 0, I'm going right 1, up 0. 2, -1, I'm going right 2, down 1. And then 3 is undefined. 4, 3, so right 4, up 3. And then 5, 2, so right 5, up 2. And then 6 and 1 2/3, so 6 and up 1 and 2/3. And then when we're ready to draw those graphs, just make sure that at some point you draw the asymptote so you can see where your graph is supposed to finish. Remember, it's not supposed to cross those lines, it's just supposed to get very, very close to them. Okay, and then we talked about how our horizontal asymptote, the flat one, was shifted up 1, so now it's at y equals 1. And then the vertical asymptote has shifted right 3, so now it's at x equals 3. And then the domain and range is going to be dependent on the asymptotes. So for my domain, it's still x is within the set of all real numbers. Except x can't be 3, because we're saying there's an asymptote at x equals 3. So x cannot be 3 because I'm saying there's a line there that it's never going to cross. And then for range, it's now f of x is within the set of all real numbers, except f of x can't be 1 because I have an asymptote at y equals 1. So f of x cannot be 1. Okay, so example 4, we're going to do this same problem in 2 different ways. So for example 4, the function is f of x equals 3x plus 5 over x plus 1. So the first option is to leave it in this form as is, and just find the asymptotes. So I'm going to compare this back to this function that we just did. So we had k of x equals 2 times x minus 3 plus 1. When you just have a constant in the numerator as opposed to an x or any variable, that's when you can just look at it in terms of translations. Like this is our horizontal translation in the denominator, and this is our vertical translation out after it. But when it's not like that and you have an x in the numerator, it's a little bit different. So it's up to you to be able to tell the difference eventually. When it's in this form and we have an x in the numerator, in order to find the vertical asymptote, when this applies, actually, the vertical asymptote applies in any form, but the vertical asymptote is always whatever makes the denominator 0, because that's undefined. So vertical asymptote, it's what makes the denominator 0. So in this case, what makes the denominator 0 would be x equals -1, because -1 plus 1 would be 0. And then the horizontal asymptote is always the coefficients of x. So this coefficient of the x in the denominator is 1. So my horizontal asymptotes would be y equals 3 over 1 as my coefficients of x. So one more time, horizontal asymptote is the coefficients of x. And this only applies when we have an x in the numerator as well as in the denominator. So in this case, my horizontal asymptote would be y equals 3 over 1. which 3 over 1, reduces just to 3. So y equals 3 would be my horizontal asymptote. Okay, so we can draw those and then begin filling in our table. So our vertical asymptote is whatever makes the denominator 0, so it's x equals -1. And then our horizontal asymptote is the coefficients of x, so 3 over 1, or just 3. And then same thing as before, when we create our table, we want that vertical asymptote to go in the middle of our table. So our vertical asymptote is x equals -1, so that's going to go right in the middle of the table. And then we'll go up, or sorry, down from there, so down to -2, -3, -4, and then 0, 1, and 2. If you printed the notes, don't worry about the bottom line, it just has an extra line. Okay, so we'll substitute in each x value and evaluate the function there. So when it's -4, and you can write this out in more steps or less steps, whatever you need to do. So when x equals -4, 3 times -4 is -12, plus 5 is -7. And then -4 plus 1 is -3. So this ends up just being, it's -7 over -3, or just 7/3. And then when x equals -3, 3 times -3 is -9, plus 5 is -4. And then -3 plus 1 is -2. So -4 over -2 is +2. And then when x equals -2, 3 times -2 is -6. Plus 1 is plus 5 is -1. And then -2 plus 1 is -1, so -1 over -1 is +1. And then plugging in -1 is undefined because it's -1 plus 1 is 0 in the denominator, so this is undefined. That's why we put that one in the middle. And then when x equals 0, 3 times 0 is just 0, so, plus 5 is 5 over 0 plus 1. So 5 over 1 is just 5. So when x equals 0, f of x equals 5. And then when x equals 1, 3 times 1 is 3, plus 5 is 8, over 1 plus 1 is over 2. 8 over 2 is 4. And then for x equals 2, 3 times 2 is 6, plus 5 is 11. Over 2 plus 1 is over 3. And any of the improper fractions, feel free to write them as like a mixed number if it helps you graph it. So 7/3 is 2 1/3. And then 11/3 is 9 2/3. Wait, sorry, I don't know where the 9 came from. Oh, because I was multiplying. Sorry, 11/3 is, I'm really tired, brain dead. 3, there we go, because 3 times 3 is 9, and then 3 2/3. Sorry, that took much longer than I should have. Okay, so now we can plot all those points. So 2 1/3, or -4, and then 2 1/3. So I'm going left x, and then, left 4, and then up 2 1/3. And then -3, 2, so I'm going left 3, up 2. I'm supposed to go one more over for the 4, and -4 2/3. Okay, so -4, and then up 2 1/3, and then left 3, up 2. And then -2, up 1. And then 0, 5. And then 1, 4. And then 2 and 3 2/3. And then we can go ahead and connect those points and kind of just follow the asymptote to finish it. Okay, and then just, sorry, to go back up, just a couple of notes from like just x-intercepts and y-intercepts in this case. So if you need to find the x-intercepts and the y-intercepts of any function, the x-intercept is what x value makes the numerator 0. Because with x-intercepts, it's when the y-coordinate is 0. So if we can get the numerator to be 0, that makes y 0 itself. That's the only way. So some of them won't have x-intercepts. And then to find the y-intercept, you just have to reduce the constants when it's in this form, and I'll talk about that in a second. Okay, so to find the y-intercept, you just have to reduce the constants, because if you find x equals 0, then f of 0 cancels out both of the x coordinates. So like if our function is f of x or not x coordinates but x terms, if our function is f of x equals 3x plus 5 over x plus 1, substituting in x equals 0 cancels out this term, and you're just left with the constants. And then you would reduce them to get the y-intercept. Okay, so there's one more way, or like one more strategy that you can use in order to graph a function that has like the x in the numerator like I was talking about up here, and that's to change it to the other form using either long division or synthetic. So option 2, it says put the function into the form f of x equals a over x minus h plus k, and this tells us our transformations, and then graph the function like we did in example 3. So if we want to take this function itself and switch it around to this form, we just have to use synthetic division. So if the function is f of x equals 3x plus 5 over x plus 1, or you can use synthetic or long division, it doesn't really matter. It'll change it to this form automatically. So if we use synthetic, we're dividing by, it's just 3x plus 1 divided by x plus 1. So this is like x minus k, basically. X minus k. So k would be -1. And then our coefficients go across the top, it's just 3 and 5. So you bring down the first number, 3, and then -1 times 3 is -3, and then add these two, 5 plus -3 is +2, and then so 2 is our remainder, and 3 is our constant. So our final answer, if we were to rewrite this, it would be 3 plus our remainder 2 over x plus 1, what we divided by, and then we can just flip this around in order to get it in this form. So we can rewrite it as f of x equals 2 over x plus 1, and then plus 3. And you can use, like I said, you can use synthetic or long division. Both of them work perfectly fine. But now we can see that this graph is going to be shifted left 1 and up 3. And we already graphed this one. I'm not going to go back and regraph it. But we can see their asymptotes shifted left 1 and then up 3 for the horizontal one. And we were able to finish our graph that way. To be perfectly honest, like throughout this chapter, we're probably not going to move away from graphing with the table. The biggest thing is you have to be able to find the values that go in the table itself and the asymptotes. So that's where like these two different forms come in, is there's different ways of finding asymptotes for each. So when it's in this form, when we have an x in the numerator, the vertical asymptote is whatever makes the denominator 0, and then the horizontal is the coefficients of x. So just the numbers out in front of x reduced. And then if you change it to this form, or if you're given in this form, you can see the transformations. So this is a horizontal translation, so that would shift the vertical asymptote left or right. And then the plus k is a vertical translation, so it would shift the horizontal asymptote up or down. Okay, so example 5 says graph g of x equals 2x plus 5 over x minus 2. So I'm going to leave it in this form, and we'll just find our horizontal and vertical asymptotes. So the vertical asymptote is whatever makes the denominator 0. So it's, in this case, it's x equals 2. And then for our horizontal asymptote, it's the coefficients of x. So this one is 1. So our coefficients are 2 over 1. So our horizontal asymptote is y equals 2 over 1, or just y equals 2. So we can draw those. So x equals 2 and y equals 2. So x equals 2 is our vertical. And then from there we can create a table, or you can just kind of plug in points on either side of the asymptote if you prefer not to use a table, but I think using a table is the easiest way. So I'm gonna pick 7 numbers, but x equals, or our vertical asymptote is gonna go in the middle, so x equals 2 will go right in the middle. And then we'll go up to 1, 0, -1, and then down to 3, 4, and 5. So when x equals -1, it's 2 times -1, so -2 plus 5 is 3, over -1 minus 2, so over -3. So -1. And then when x equals 0, it's just 0 plus 5, so 5 over 0 minus 2, so over -2. So -5 halves, and that's also going to be our y-intercept because x equals 0. And then for x equals 1, it's 2 times 1 plus 5, so 7 over 1 minus 2, so over -1, which is -7. When I plug in x equals 2, it's undefined, so that's just our asymptote. And then when x equals 3, 2 times 3 is 6, plus 5 is 11, over 3 minus 2, so over 1, so just 11. And then when I plug in 4, 2 times 4 is 8, plus 5 is 13, over 4 minus 2, so over 2, so 13 over 2 turns into 6.5. And then when I plug in 5, 2 times 5 is 10, plus 5 is 15, and then over 5 minus 2, so over 3, and then 15 divided by 3 brings us down to 5. So we can plot those points, so -1, -1, and then 0, -5 halves, so it's -2.5, and then 1, -7, and then 3, 11, that's up off the graph, 4, 6.5, and then 5, 5. And if some of your points fall off the graph, that's okay. Just make sure that you're following like the asymptotes to finish drawing your graph. Just know that like your lines should get very close to them, but they should be like a nice curved line. Okay, and then the last problem is example 6. It says a company purchases a blueprint plotter for $1,500. The plotter cost for each set of blueprints is $25. The first one is we're going to write an equation to represent the average cost of a blueprint plotter. So we'll call our average cost C, and we want to write an equation that represents the average cost. So we know that we were going to pay $1,500 for the blueprint plotter. And then we know that each blueprint cost $25, or each set of blueprint is $25. So 25 times, we'll say X is the amount of blueprints that we're going to print. So 1,500 plus 25 times the amount of blueprints we print. So right now, this is the total cost that we're putting in all together. So we spend 1,500 on the plotter, and then we spend $25 per set. So that's our total, that's how much we're spending all together. And then to find out the average per blueprint plotter, we have to divide by X. So divide by the amount of sets that we're printing. So our cost is, we paid $1,500 for the plotter. We're spending an additional $25 per set. And then if we want to find the average cost, we have to divide by the amount of sets that we're printing. And then for part B, estimate how many blueprints must be plotted for the average cost of blueprints to fall to $75. We want our average cost to be 75, so that means that 75 is going to go in for C because that was our average cost equation. So 75 equals 1,500 plus 25x over x. And then in order to solve, there's a couple of different ways that we can do it. We can multiply both sides by x. We can kind of separate this into two different fractions if we want. I'm going to multiply both sides by x to cancel out dividing by x. So I'm going to multiply this side by x and this side by x. These will cancel out. And I'll be left with 75x on the left side equals 1,500 plus 25x. And then we can solve for x, we can get them on the same side, so subtract the 25x over 75x minus 25x is 50x equals 1,500, and then I'm going to rewrite that up here. So 50x equals 1,500, and then the last thing I need to do is divide both sides by 50 to isolate x. So 50 divided by 50 cancels out, and we're left with x equals 1,500 divided by 50 is 30. So that means we'd have to print 30 blueprints in order for the average cost to fall to $75. And then for part C, what happens to the average cost as more blueprints are plotted? So this one helps if we rewrite. I mean, I think we can kind of like make a really good assumption about it. But looking at this equation and rewriting it as kind of like an equation that shows us transformations will really help us show or see like what's happening to the average cost. So what I mean by that is I'm going to take the cost equation that we created in part A. So 1,500 plus 25x over x. And I'm just going to divide these both by x in order to rewrite it as a transformation. So in order to divide both sides by x, whenever you have like two different terms on top of the same numerator, if you want, you can separate it into two different fractions. So c equals 1,500 over x, and then plus 25 over x. So I just took the two different terms and put them over their own denominator. It's the same thing. And then, of course, these x's cancel out. So then we can rewrite this equation as c equals 1,500 over x, and then just plus 25. So the way it's written right now, we can kind of see these transformations. It's a little bit more like there's no horizontal translation there. There is a vertical translation of 25, but we can think about like as our like number or as our blueprint printed goes up or plotted goes up, we can see that this number may get very, very close to 0, but it's never actually going to equal 0. So like if I print like just thousands of blueprints, like the more blueprints I print, the higher this x value is, the smaller this fraction becomes. Like 1,500 over 2 is a lot larger than like 1,500 over like 10,000. So the more blueprints I'm plotting, the smaller this number gets, and the closer the overall cost gets to 25. but it's never gonna get to 25 or get below 25 because this like 1500 over x can get infinitely close to 0, but it will never get to 0, and it'll definitely never be negative because I can't have like an average amount printed. A negative average amount printed, a negative amount printed, a negative x value basically. So this will just get very close to 0 without actually crossing it. So the cost approaches $25. So sorry, last time, the more higher my x value is just saying the more blueprints are plotted. So if the higher the x value, the smaller this fraction becomes. This value, the overall cost, gets close to 25, but it doesn't actually ever cross it or ever actually get to $25. So the cost approaches a $25 average.